Welcome to our NPTEL courses on power quality improvement technique, that is the 3-phase. First of all, today we will discuss about the problem of this power quality due to this 3-phase converter, and thereafter we shall talk about the multi pulse converter. First we will talk about the 6 pulse converter for different kind of load and its THD and its solutions with the multi-pulse converter. So, it is quite elementary. This is the we have chosen, you know, that for the till now in many industrial drive, because predominantly we had a DC motor for traction for railways, let us say, and these are the quite heavy machines, and its rating. For this reason, till now they are using this kind of control rectifier, and we just revisit the control half control rectifier. So, with the free wheel, and you know these waveforms quite well in your power electronics courses. What I wanted to say here, that we assume that your load current is highly inductive, thus you have a square wave and that will be transmitted into the AC side also as a square wave. So, these are the line voltages, and these are the, because this is the duration alpha, and where alpha is more than pi by 3 60 degree, that means it will start from this point, and for this reason at this duration T1 and D1 will conduct, and you will get a voltage that is equivalent to the VAC. Similarly, there will be a durations where free wheel will occur and you will not get any voltage. It is better to have a free wheel into the system, otherwise you will have a negative portion of it, and then what will happen, due to that you will get a poor power factor. So, that is not advisable, and for this reason we want that free wheel to be placed. Free wheel improves the power factor, and what about the power quality, we will discuss consecutive 2 to 3 classes how it can be further be enhanced. So, this will be your output voltage profile, and so this is your output voltage profile, and this is your when T1 and D1 conducts. So, this will be the current for phase A, and similarly this will be the current in phase B, this will be the current for the phase C, and of course, if you see that the current I1, then this current will be in a positive and this current will be negative. Same way you will have a phase B and phase C, or 1, 2, 3. So, thus when it is quite elementary, just for the recap I am just telling, let us take T1 is been triggered at an angle alpha plus pi by 6. So, T1 and D1 conducts, and simultaneously, and the output voltage VAC will appear, and at omega 7 pi by 6 AC VAC becomes negative, T1 and D1 are turned off, and free wheel actions takes place. If DM is not used, T1 continues to conduct until T2 is triggered, and thus you will have a negative portion of it into the load voltage, and this will essentially what will happen, you will degrade the power factor, and at omega t equal to alpha plus pi by 5 pi by 6, free will again complete for the T2 D2. Now, we have to have some parameter to be analyzed. So, you can have Vm there are 20° phase shifted waveform, and Vac equal to Van minus Vcn. So, ultimately you get root 6 V sin omega t minus pi by 6, and if you integrate over it, they will get 3 such cycles. You will get the average power and you get the RMS value of it, you have to integrate over dt. So, thus the input power factor is a important quantity, and this important quantity is the active power by the RMS input power. Once you have a negative portion of it, the active power essentially will be subtraction. So, if you have this portion of it in a without free will, then what will happen? Effective average value will come down, and thus input power factor will be lowered, and this is expression of it IPF, I voltage average and the current average by 3 Vm Im RMS value. Now, for the 3 phase full wave half control rectifier, these are the all waveforms you have studied into the power electronics. So, we start from this point for continuous and for alpha less than 30°. So, ultimately you can have, you triggered at alpha here T1 D3 will conduct. So, you get the voltage first CB, thereafter AB, thereafter AN, thereafter CN, AC, like that you will get the waveform. So, this will be the current through the thyristor T1, this will be the current through the this will be the current through the diode D2. Similarly, you can have the current, this is the thyristor T1. If you combine, this will be the phase current, and you can see that the symmetry is lost. Previously we had a symmetry, and ultimately, so you got this kind of input current, that is the our contention now. So, you get this kind of square wave, and you know here this point is little more, it is pi by 6 plus alpha, and this point is quite less. So, you have a asymmetry, but if you go back to this circuit, generally there was no asymmetry. Okay. So, we have to do the Fourier analysis of this waveform and ultimately come out that what should be the harmonic content of it and what is the THD of it and how we can mitigate. Of course, we cannot use thyristors, we have to go back. If you use thyristor, we have to go for the different solutions, but apart from that we require to visit it how to mitigate this problem. So, this is the 3 phase phase shifted voltage, and ultimately VAB is VAN minus VBN equal to root 6. If you add these two, will be root 6 sin omega t plus pi by 6, and VAC will be root 6 V sin omega t minus pi by 6. So, you can get the average value. So, you have to have a 3 such pulses. So, 3 by 2 pi, pi by 6 to pi by 2, where you will have that voltage VAB, thereafter you will have a voltage VAC, and you subtract it, and ultimately you will have the average voltage and the RMS voltage. Now, this is the problem of the converter. So, why to use the multi-pulse diode rectifier, and because we can see, we will find, I will show a little later, that THT, current THT will be around 30%, and to improve the input power factor you will have a voltage, you require to have a also close to 0.95, and to avoid the semiconductor devices in series, so that it may damage severely, because if you have a so much devices in series, then turning on, if there is a delayed, whole stress will be on the another devices, and thus device may be damaged. But that is not the case of the multi-level inverter. We shall separately discuss about the multi-level inverter. So, and its applications of the power quality. So, that is will come later, but let us talk about this 6 pulse diode bridge rectifier, and ultimately what you get is the VAV, and that is the simplest circuits we can have in the 3 phase, and this one is your root 3 VL sin omega t minus 6. And similarly we can calculate, ultimately you can see that current pattern, instead of the square wave we will have this kind of waveform for resistive kind of load, but if you make this current RL, so you can get a straight line also for the inductive kind of load. So, ultimately as you have seen that for the durations it will start in a conduction mode, because it is equivalent to alpha equal to 0. So, it will start into the conduction mode when D1 and D6 is starts conducting, and thus you get the area A1 by pi by 3, that is 1 by pi by 3. You can apply these integrations, pi by 6 to pi by 2 root 2 VL sin omega t pi by 6 d omega t equal to 3 root 2 by pi omega line to line voltage, that is the 1.35 of the line to line voltage that will appear as a DC voltage in case of the diode bridge rectifier. So, you can calculate what is the line to line voltage in RMS, just multiply with 1.35, that will be your line your DC average voltage. Now, this is the case once you generally you want a constant DC bus voltage, and due to that you require to put a huge capacitor, and once you put a huge capacitor then it becomes constant. In that case what happens, that is the quite detrimental, because current will flow once this VAB crosses this value of the VDC only for that much of duration. So, current will be only for this much of duration, again it will be flowing for AC when it is go high for these durations, similarly for BA and the CA and so on. So, thus you got a problem of the shifted power factor or displacement power factor. So, for this reason you can see that this is IA, IB, IC, and it will have a rather more nasty THD for the capacitor, and it can go as high as 70% for the light load. So, this will be the diode current ID, and that will be like this, where D1, D6 conduct, D1, D2 conduct, and so on. Now, how you will calculate the conduction angle? So, this is the sin theta 1 will be BD by under root of VLL, where it is theta minus pi, because you cross over here, then diode becomes then this D1 will be forward biased and current will flow. Again at this point it will be reverse biased, current will not flow, but what happen, it is for the VAC, again this phenomena will occur. So, ultimately this will conduct till this time, that is for the theta 2 to theta 3, and there will be no conduction for this time. Again it will pick up in this duration when AC again crosses the capacitor value, and due to that, so this will be the nature of the current, and this is a worst condition rather, and you got a you might be the charging the battery, and that is a quite common applications that we will be doing. And there what happen, you can see that this is the different current has been shown. This is IA, this portion L is IA, and I just take a different color pen, maybe blue. So, this is IB, sorry, this is IC, and this one is IB. So, ultimately this will be the current profile and its THD is equally bad. So, once this is the overlapping region where 3 devices conducts. So, D1, D2, D3. So, D1 and D3 for the upper leg and D3 from the lower leg. So, what happens then with the increase in the load current, the rectifier will enter into the discontinuous current operation. During the commutation interval, that 3 diodes are on, that is the one of the issues. So, you have a more conduction loss also, because please understand that every diode, these are all power diode, it is not the simple signal level diode that you have a 0.7 volt. You may have this voltage drop because of the more epitaxial layer of the plus n region. So, you can have this drop maybe 1 volt or 1.2 volt if it is carrying 50 ampere of current. So, 3 diode it is carrying 30 ampere 3 volt each plus 50. So, it will be 150 watt will be lost due to that. So, this system is also quite inefficient, apart from that is a problem of the power qualities. So, this is something that waveform we can see that this is an example of the 6 pulse diode based rectifier, and the rectifier rating is of this much volt, 60 hertz and 2 MVA. So, base current is this much ampere and the base inductance is 22.9 millihenry, and line inductance is this much per unit and line current. So, this is the profile of this, and ultimately this is the fundamental of this current, and you can see that this is the I1 when it is a per unit loading is less. So, you have that 63% of this harmonic, fifth harmonic, and it is a also negative sequence component some extent. Why? Because if you sit on the 6th harmonic with respect to it is a negative sequence. So, this is a 7th harmonic, this is a 11, 13 and so on, we consider the 3-phase system. So, multiple of 3 is absent. So, you can see that the THD as high as 75% and for the light load, and once you have loaded little bit, so it will come down to the level of 3 to 0.7%. So, we have discussed about the power quality, we have seen that restricted power quality is 5 to 3 THD. So, here you got a THD well above that the standard requirement. So, what can be the solution? So, and also we wanted to check few aspects of this. This is the effect of the THD. Source inductance, you know that effect of the source inductance, effect of the inductance, you will have a overlapping region into the line current, and thus no power will be supplied during that region, that is that angle cos mu. And due to that what happen, power factor degrades, higher the source inductance, but it is better for the THD point of view. It will try to take out, reduce the displacement power factor, and for this reason you can see that this is the A graph for very quite low source inductance. So, this is the curve while increasing the load, and this is a curve for Ls equal to 0.1 for increasing this load, and for having a quite considerable amount of the source inductance, you can see that even that THD is comes out to be close to the 5% here and is quite acceptable. And on the other hand, you can find that this at the low frequency, lower source inductance will give you a better power factor, but gradually once it close to the load increases, so that gives you better power factor. So, we can add the source inductance which is considered to be a detrimental. It is not that detrimental considering the power quality problem. So, for this reason, we can think of that a 12 pulse converter. So, this is a concept of the 12 pulse converter. We can have 18 pulse converter. For sake of time, we can have a 24 pulse converter as well as a 48 pulse converter. For sake of time, again we require to restrict our discussions on the 12 pulse converter, and you are required to go through the other method. It is the same extension of the 12 pulse converter. So, I just take the example where this angle is 30 degree, phase shifted by 30 degree, and the secondary line to line voltage VAB equal to VAB prime equal to PB by 2, and we assume there will be a, because one is star, another is delta, this primary is star, and you can see that this one is star and this one is delta. So, there will be a phase shift of 30 degree between these two lines, and ultimately they can be connected in series, and the required ratio generally it required to be N1 by N2. So, N1 is the primary side and generally it is in a distribution side. So, we expect that it would require to be step down. So, but you require the same level of voltage, and for this reason it has got more line voltage. For this reason the ratio required to be 2. Here ratio required to be 1 by 0.866 rather, n by n2 required to be 2 by 1.732. So, it will be little higher than 1. So, in that way you require to fix up the winding, and you see that what happened then. So, this is the first, this is on the waveform for the first converter, that is IA, and for the primary, and this one will be essentially for the IA prime, and ultimately this has to be added up. So, this waveform and this waveform required to be added up, and ultimately if you add up you get this waveform, that is as your input. So, as you know that there will be a fundamental as well as fifth 7, and there will be a fundamental and the fifth and 7, but they will cancel out since they are 30 degree phase shifted. So, thus what happened, fifth and 7 of equal magnitude, but in opposite direction will cancel out, and ultimately you will have 11 and 13. So, what happened? So, in the start side of it the primary, you will not have any 11 and 13. So, you can see that. So, due to the absence of 11 and 5th and 7th harmonic, the THD has been increased to 8.38%. So, that is close to your 5% standard. So, some way it is acceptable. So, if you want to have a more, then we require to go for the 18 pulse converter. So, design, you require a typical design, and thereafter you can have a your 15-degree phase shift for the for this 24 pulse converter, and also you can go for the 48 pulse converter. Let us see that what are the changes or the loading of the THD. You know, while source inductance being 0, that is a, but that most unlikely, but there we can consider a heavy inductance, but it is quite low inductance. So, this will be the THD. Ultimately, if you load it, it comes close to the 8%, that is what has been mentioned in the previous slide. So, if you have a little more source inductance of 0.5, so it will come to around 0.6, and generally it is present, and thus you almost get into the 5% standard, and if you have added around 5% inductance, so you can see that you can well above to the requirement. Same way there, and with a leakage reactance of 0.5%, because it is generally present here because of this transformer. So, similarly you can have A, that is the THD is being fed to 0. So, if you load it, so there will be a little drop because of the leakage reactance is present, that is quite normal. It will drop in the overall power factor, but we do not bother about power factor if it is close to 0.9, but it is well above 0.9. So, for this reason this solution is accepted to us. So, at B gives you little close to 0.95, and C gives you little bit less than 0.95. Thank you for your attention. I shall continue to your discussions about the different topologies. Thereafter, we shall visit that 3 solutions, because this is one of the solution of for the for this 12 pulse we can have solution with the 18 pulse as well as 24 pulse, 48 pulse, but designing constraint is quite complicated, and you require to have and the solution is quite bulky. Instead of that, we may look for the power electronic solutions in based on the 3-phase PWM rectifier that we can see, and we can find also its applications. So, we shall continue our discussions first of the problem of the 3-phase power converter, and from this diode based rectifier we prefer, because it is also, you can see that it is quite simple because it uses the diode based rectifier, but it is a 12 pulse rectifier. So, same way we require to change the transformer pattern, and we can have a 18 pulse converter. Same way we can have a 24 pulse converter, and so on. So, this is the some observations and some portion of the mitigations of the power quality by multi pulse converter. Thank you.